Started recording. Okay, well, we can do whatever you want, but he hasn't talked about any of this in class at all, right?
No.
Okay, that's what I thought. That's funny. Because there's only one class that I wasn't there for, and it was when you took the quiz, and he just talked about Young's modules, like that kind of stuff.
Yeah, you
right?
started that off. Last
all right.
week was the fracture theory.
Yeah, that's right. Okay. All right. So what do you want to?
So dive right into it, but it asks for the expressions for velocity and acceleration, simple harmonic oscillator using the forms of equation 6.3,
Okay.
and show that the velocity v is 0 and the oscillator position x is maximum.
Yes.
I understand that, absolutely.
Yeah.
I understand that, but showing it
Okay.
like algebraically?
Yes.
Yeah, no.
Okay, this is nice. I like this. Okay. So, a simple harmonic oscillator. I would start to understand it by looking at the differential equation.
Okay.
Because you could do basically all the problems. You could probably do every single problem in this chapter by just using the solution to the differential equation, which is the actual formula
Okay.
for how it moves. And so you might be tempted to be like, if I don't need this differential equation, which, yeah, again, you don't, I guess, really, but I would like to, I think it's better to see it. Actually, I'll just use x instead. So, actually, do they put the a equals k? I think they use k, right?
Here?
Do they have it here? Yeah, minus k. Okay, so make sure I get this. I guess it has to be minus k. Okay, so this is the equation. Actually, I mentioned this a little bit. I don't think I called it, use the same language, but in the one of the math reviews I mentioned, I don't even know if I wrote this on the board. Anyway, something like this.
Mm-hmm.
But anyway, so all this says, this is actually, you get from this. So this is a force, okay?
Mm-hmm.
And if you have an object with just one force on it that moves in the x dimensions, this is all one-dimensional. So we're not, even projectiles were like two-dimensional. So this is even actually a little simpler in terms of like you don't need two separate equations kind of thing. So you have a one-dimensional force, you have an object with one force on it, but this time the force is proportional to x, which is the displacement. So let's say you have an object, and we're going to set the reference frame to have x be in the middle to be 0. I mean, technically you sort of automatically get a reference frame from this because there's one point where the force is 0, and that's defined as being x equals 0, right?
Okay.
So we'll pick a point where if you left the object there, it would stay on its own. Now we have a force, and now this is unlike every other force we've had in free body diagrams because all the other forces generally have been constant. Like gravity is just a constant force. Friction is constant. It might depend on things, but it'll be constant over like the time evolution of the system or whatever. So, but this is actually variable. This means it depends on the actual position of the object. So if we put the object here, we're going to get a force, and this is like just a constant. Yeah, exactly. You could call this a positive constant.
Okay.
It's okay to, yeah, it would have to be a positive constant. And this minus x means that if we go in the positive x direction, we're going to get a force in the negative x direction, right? If we put a positive displacement, we're going to get a negative force. That means we get a force going this way. And if we go to a negative x position, we're going to get a positive force, exactly. So
Gotcha.
Force going this way. So now you can kind of automatically see what that is going to look like. If you push the object to the right, the force is going to go opposite your displacement. That's literally what this minus sign means, right? And so now we don't necessarily know anything about what the behavior is going to look like if we do things to it. We'll see what it looks like, but that's good intuition because, of course, if we had, let's say, a plus sign here, that seems like a very similar type of problem. It seems like, oh, well, we can just think of that as like k is negative maybe, right? Or like, it's very similar if we had a problem with it's plus. But if it was plus, that means that if we like push it over here a little bit, the force would push it out. But then if it's force pushing it out, it's going to keep it like it's like something on a, like if you had like a really steep mountain and you put something on top, any push is just going to roll up to infinity, right? So that wouldn't be interesting at all. I mean, you could write an equation for it, but it wouldn't really tell you anything. So the fact that it's a minus sign seems like a very minor thing. Like, it's like, oh, it's just one type of example. But this is the one that's actually interesting because this tells you that the dynamics are going to be sort of contained or something like that. It's going to do something complicated.
Okay.
It's not just going to go to infinity in one dimension or anything. So anyway, this statement here, so I'm going from here to F is MA, right? Generally when we write free body diagrams, for the most part, the homeworks and stuff have been basically you set the net force to be 0
Mm-hmm.
because it's not accelerating or it's not moving at all or whatever. Of course, in general, like we saw with the pulleys and the blocks and stuff, you actually really want to set it to equal to MA, right? And of course, sometimes MA is 0 or A is 0, but always it's equal to MA. So we could do that. And M is just the mass of the thing, and this is all the same. Now we have to, this is a differential equation, MA equals KX, because A and X are actually related, right?
Okay.
A is not just a separate variable, because as X changes, that's a velocity, and as velocity changes, that's the acceleration. And the precise mathematical way to write that, how that relationship works, is like this. It's just that we'll say velocity is of course dx dt, right? These are technically vectors. I'm not gonna. The vector doesn't really matter because it's one dimensional. But in general, this equation you can only, you could define it more generally. You could have a multi-dimensional harmonic oscillator that you might have the restoring force in one dimension, or you might have the restoring force in all dimensions, right?
Mhm.
Actually, we might see that with quantum mechanics. I'm not sure. If you go to the hydrogen atom, there's like kind of a potential and electrons. Anyway, so spherical harmonics, those are really cool. They're essentially this. Well, I'm not going to go into it, but they're essentially the same as this, but in 3 dimensions in spherical coordinates. Anyway, but so V is dx dt. This is literally a definition. This isn't like a deep statement. And A is the definition of A is dV dt, which is of course just dx, the second derivative of x dt squared. Right. So of course these are not results. These are just definitions. So using the definition of A in the x, of course these are all in the x direction. We can write this more clearly as a differential equation where now we only have the one variable, right? And we see that x is a function of time, of course. That we can only write dx dt if it's a function of. If it wasn't a function of time, it would be 0, right? Like if it wasn't a function of time, the acceleration would be 0. That's what it means as a constant position. Anyway, so this is all we've done is say if we have an object with one force on it, and the force is actually proportional to the position. So the farther you go, the more the force you get. I should have said what this probably is, which I think it's in the book somewhere. But you could think of this as like a spring,
Okay.
right? That if you had a spring with some fixed length, actually they might even write. Some books write this as L minus L naught, right? Or
Oh yeah.
oh
Okay.
yeah, where L is
New
really
length.
X.
Your new position against your.
Exactly, because most real life springs. So this is like an idealized example.
Okay.
This says that you have an invisible force such that if you go negative and positive, right? But for most real springs, it has a fixed length that if you just don't put anything on it and let it rest, it'll be at L naught.
Yep.
So if you plug in, if you put a block at position L equals L naught, you'll get 0 force. Those are sort of equivalent things. But if you compress it, that's saying that your length of the spring. So this is literally the length of the spring. This is more of a physics way to write it, where you write the displacement from a arbitrary starting position.
Mhm.
This is more of a measurement of an actual physical spring. Again, these are exactly equivalent. It's just that we're setting x to be, I guess, L minus L naught technically. That's sort of more complicated than it needs to be. But this is just from a spring that has a resting length L naught, and then when you make it a length L, which could be smaller or larger, you get a responding force, and you can see that's exactly what it is. If you compress it, that means this is smaller than this, so that means this is negative, and this is negative, so therefore this is positive,
Mhm.
and you get that it pushes you, right? Like to the right, so it's positive. And if you stretch it, this is bigger than this, so this number is positive times a negative is a negative, and you get that it pulls you. So it's a perfectly symmetric spring in the sense, symmetric I mean in the sense that compression by, 1 centimeter and extension by 1 centimeter have the same exact force. They're just in opposite directions. Now, of course, in real life, there's all these things. It's called Hooke's law.
Yep.
So yeah,
I remember.
if you've probably heard that. This is called Hooke's law. Now, I think a lot of people, well, I should say a lot of physics majors who see this, and I know a lot of them, see this and think, okay, well, this is like one of those dumb approximations that physicists make, that like in engineering you would never really do something like this. Like this is just to make physics problems easier because you can get this equation. Well, this is literally, we don't, again, this is not really necessary to do any problems in this, but this is technically like a Taylor expansion. Right, we could have a term that's like, so we could have something that's like x squared, and it has a very small, like, in real life, a spring, if you compress it to where, like, the coils are touching, you've sort of broken down this completely, because now it's not really behaving like a spring anymore, it's like a block of metal or something. You know what I mean? It's like, you clearly, this gets broken down. But you could model the actual behavior, and also, like, if you stretch it enough, it, like, deforms a little bit, and so you could actually write the behavior with like higher order terms, but if you just take the lowest order term, it's approximately basically linear, which is this. So it's essentially a Taylor expansion. So that's just the reasoning why we use this. It's not like we're pretending that springs behave like this and they really don't. It's that they do to first order. So again, the whole moral of all these Taylor expansions and approximations and stuff is that things that really behave sort of linear, like the force really is linear to first order, you can approximate like just with this term. You don't need to include the higher order terms. And of course, then you have to say that every result you get is really only true in small regions, right? Just like a Taylor expansion is only true, it's only a good approximation, in a very sort of narrow, right? And of course, depending on how you're actually, I don't know about real springs, but it's perhaps true that this is actually a very good approximation to large distances. So whatever. I think it really is. Like there exist springs that really do behave like this to very good approximation. So It's not a crazy thing to do. Anyway, so this is sort of a physical measurement version of that. But anyway, okay. So so now this is a differential equation, and now you could do some methods to solve it. You could plug in, you could look up some ways to plug it. You plug in x to be a test solution and then solve for some constants or whatever. Basically, you would get that if I'm going to write x double dot for this, the second time derivative, is minus k over m x. And now this has a solution. Now again, if you've done multiple differential equation solutions, recently, you could probably see that, well, what function do I remember that has the second derivative proportional to the function itself? So of course this is a constant, but this statement says that the second time derivative of this function x of t has to have that same function appear in the result. And we know the exponential does that, right? That's an example. But the important part is that this is a minus here. So if we put an exponential, we could actually, that would be totally valid. We would just have to make sure the exponential, when we take two derivatives, gives you a minus sign. Well, that means that whatever we put in the power, when you do two of them, you have to get a minus sign. The only solution is I, right? Now, that would work, and we could use the Euler formula or whatever, but we could sort of do it more directly by saying, exactly, cosine sine. So I'll use just cosine. And you could, if you do the thing out, you could see that there's a cosine and a sine. And by the initial conditions, I'll tell you what I'm making in a second, but by the initial conditions, let's say at the time 0, it started at some position. Oh, okay, actually, no, I'm not gonna do that. I'm gonna say, well, okay, I'll just say this for now. Well, no, I'm not. I actually will say it more generally. So the general solution would be like A cosine omega t plus B sine omega t. And the reason is because there's two solutions. There's sine, also has the same exact property, right? So they're both valid. But what you can actually do is this, so sine and cosine, so cosine's like this, and sine's like this. They're only different by phase.
Yeah.
So you can actually say, I have two unknowns here, and I can actually change them into these two unknowns. a and phi, the phase,
Okay.
and this is actually equivalent. Equivalent means that that I can any function that I can express like this, I can also express like this. Right. So in other words, that means that all I can express with this equation here. Remember, they're the same frequency, so it's not like I have two separate waves here. This is one wave where I have some component that starts here and some component that starts down here, and all I can do basically is like shift it, so like I can get this. So this is like a sort of half shifted.
Yeah.
Right?
Pi over 2.
Yeah, exactly, or something like that. So this I could express this in this form, but I could also just say it's a cosine, but with a phase.
Oh,
The phase
yeah,
just
right,
shifts it.
right. Okay, I remember that.
Right. So this just shifts it to the right or the left or whatever you want to call it.
It would be positive to the left, right?
To the left, yes,
Yeah.
because it would because 0 would then be farther ahead, kind of thing. So anyway, I don't. Okay, maybe
I
I'm.
don't remember how to do
May-
it.
you're-
I just remember positive moves left. So.
Yeah, I think you're right. Yeah. Yeah. So this is a phase. So these two are equivalent, and I actually kind of like this one. The reason is because, first of all, there's one wave. I should say sorry. When you so let's just actually do the plug this in and just make because I put an omega here, and of course you can kind of see what it's going to be. But if we take two derivatives of this, so if you want to write it out, please do. But I'm just going to do two at once, which is where we take two derivatives and we get a minus sign with just one omega, and then we take another derivative and we get an omega squared cosine omega t plus phi. Now this a cosine omega t plus phi is x. So this is minus omega squared x, right?
Oh, that's all. Yeah.
I just
okay. Yeah,
I just
get you.
rewrote it,
I
glitch,
get you.
but yeah. So this literally is a. Sorry. Oh no, sorry. This literally is x. That's what I meant. Now you can see that this is minus omega squared. I want it to be minus k over m, right? Like I just made up omega, but to match this implies that omega squared, I should say, should be. Skipping a step here. K over m. If omega squared is k over m, this perfectly matches. Right? Remember, note it's positive because the minus sign's already here. So this is x double dot, right? X double dot is this of my test function, and I'm setting my test function. I have to solve for this to get my test function to actually solve this equation. So omega squared is k over m, which means omega must be radical k over m. And they're both positive. Mass is going to be positive, of course, and k, I said before, has to be positive, otherwise it wouldn't make any sense. It wouldn't be a Helm oscillator. So this is totally fine to do. It's not going to be a complex number or anything. It's just a real number. Okay. So, and you could write it. So if you want, you could write it as cosine radical k over m t plus phi. You could write that, I guess. People usually write omega because sometimes you actually might need to talk about the frequency. Omega is going to be the frequency. So anything that multiplies time and has nothing else. So another thing, when I check units and stuff, anything in a cosine or in an exponential or something like that has to be unitless. It can have units of radians. That's equivalent. So technically, I guess it's radians, right? But that's equivalent to being unitless, because radians are really a ratio of two distances. So, so anything that multiplies time that's unitless has units of 1 over time, which is frequency.
Yep.
So anything here you can call frequency. Now there's a distinction between omega and f. So omega is called angular frequency.
Yep. Okay.
And
that's right.
which is in radians per second, and frequency is in hertz, which is
1
1
over
over seconds. Yeah. So the only difference is because we put it in a cosine. For this to like loop back to its starting point, this has to go to 2 pi, right? Whereas usually in real life we want to talk about things in like hertz, where we don't really care about the 2 pi, so we can convert it. Basically, it's kind of like this f is going to tell you the time for one revolution.
Okay.
Right. So one cycle takes how much time? That's f.
Yeah.
Omega is going to tell you how long for 1 radian, which is not a super helpful thing to do. It's very helpful in a formula because
getting you to that.
Yeah, you could even plug in 2 pi ft. That people do that too, because if you put in 2 pi ft, that says that after after one frequency amount, you get 2 pi, like if f is like 1 over the time.
Yep.
You get 2 pi, and that's 1 revolution. So in this case, f is the time. Sorry, f is
How
not
many
the
frequencies? How many?
Yeah, sorry. This is what I really mean to say. Sorry. 1 over f is the period.
Yes.
That's the time for one cycle. 1 over omega is the time for 1 radian.
Okay.
Right? So that makes sense here. In a cosine, you'd be like, well, sure, because this is in radians. But again, it's not like an incredibly helpful thing to say what's the time for 1 radian. No one will ever ask you how long it takes for 1 radian.
Mm-hmm.
They'll ask you how long it takes for 2 pi radians, which is 1 revolution, so that's the frequency. So these are all just like things to, I don't think if they asked you the frequency and you gave them omega, as long as you wrote radians per second, you're fine.
Okay.
If they specifically asked you in hertz, right, or in revolutions per second, or cycles per second, or whatever, you really do want to put f.
Mm-hmm.
So, but anyway, I wouldn't write it in, I don't like writing it in the formula here because I think this is much clearer mathematically, because then when you do the derivatives and stuff, you don't have to worry about the 2 pi's. You would really have to put like a 4 pi squared and all this crap. So like, you could convert it and I would rather just,
Cleaner.
yeah, I'd rather just do
Yeah.
this whole thing like this. This is the angular frequency here. And if you want to find the frequency, just when you're done, do this, right? Yeah, and we can even check the units. And again, I keep saying radians don't have units, which is true, but you could still write radians per second, and that's...
People up front.
Oh, sure, yeah. Right. We are resuming. Okay, so so I'll just quickly talk about whatever. So we were just talking about if you have this is called a restoring force. Is another thing I didn't say, but restoring force meaning translation in each direction sends you back to the origin. It doesn't send you back, but it like pushes you in that direction. We can write it as f equals ma, and then we could write a is of course related to the second derivative of position. This is all in one dimension, so we can we don't have to worry about vectors and stuff. The sign is essentially the vector part. And anyway, this is a differential equation. We can plug in a solution that we know, which we could write in this other form. Instead of writing cosine and sine, which are just different phases of the same wave, right? Cosine and sine are just shifted versions of themselves. We could just write this as one single cosine with just a phase here. So this is actually the same information. Now, of course, if these had different frequencies or if these had different amplitudes, we could not write it like this. Because if they had different frequencies and amplitudes, you could get like a weird, something like this, right? This would be like one big wave plus like a smaller wave or something like that, right? So this, we could not write. This would not be of this form, though. This would have different frequencies or something. But the fact that they have the same frequency and the same, they don't have the same amplitude. Okay, anyway, that's the fact that they have the same frequency says that, okay, so it doesn't matter. The fact that they have the same frequency says that we could just write it as a single wave, which could be shifted by some amount, which we don't know yet, because I didn't say enough information to know that yet. And then, of course, I just made up omega to put as a frequency. I knew it was a frequency because it multiplies time to give something with no units, sort of. Well, it's radians, but whatever. And so once, of course, omega is not in the differential equation, so we're not done yet. So we need to actually plug in the differential equation, and we get a cosine this. This is just x, so we get omega squared minus omega squared x. Omega squared must be k over m, positive, and then omega is k over m. And we said that k over m, k and m have to be positive, so we don't have any issues with imaginary things. We could have done the whole thing with exponential, and we get an imaginary, and we'd have to convert to using the Euler thing. It would be equivalent, but anyway. So this is sort of the solution for a simple harmonic oscillator. There's two unknowns here. There's the phase, which is I didn't say anything about, we don't know yet, and there's the amplitude, right? And we know that there has to be two unknowns because we have a second order differential equation, and I didn't tell you any initial conditions. So to solve for these, we would have to give you two initial conditions, right? And it would be sort of like saying, okay, I have a spring. What's the equation? And you'd be like, you could write this, but it sort of makes sense that you wouldn't really be able to say, like, okay, well, where did you start? Like, if you just had a spring that was at rest, it would just be 0. So, like, that's not, which would be this with A is 0. So this still encompasses that, even though it's sort of a silly solution. But there's two initial conditions that we need, and I'll just give the simplest ones, which is probably the only ones you're ever gonna see, which is the position at t equals 0, right? Which just means where do you start it now? Yeah, okay. So let's say I started at, I'm gonna say A. Now this might be a little confusing, but I'm just gonna define this as A, and it's actually the same A as here. I mean, okay, I shouldn't really do that. I'm skipping a step. I'm really trying to skip a step, but I shouldn't be doing it. Let's say we would get like a distance. This is a distance, so we would get like half a meter or something. So I'll call this, what should I call it? I don't know. Well, yeah. I just don't want to, okay, I'll call it A. I just don't want to introduce more variables and then say they're the same, and it's like, well, that's confusing that you have so many variables. This is literally going to be the amplitude. Actually, that's not true. This might not be the amplitude. That's why I shouldn't say this. Okay, now I remember.
Yeah,
I'm sorry.
That's my reason why I thought we wrote A.
I'll say alpha.
Oh, okay.
It is not necessarily the amplitude, okay? If I give you the second initial condition, x dot of 0 is, now x dot is of course the velocity. So let's say the velocity at 0 time is what? Well, I'm telling you I started at some position, so it's not, this doesn't have to be 0, or it's usually not 0. Let's say this velocity is 0. That means that I have a spring, and at time 0, when I start, I pulled it or pushed it or whatever to some position A, and I didn't give it any velocity, and I let it go. Now, what you'd expect is that, now we'll plug it in a second, but what you'd expect is that the amplitude of that oscillation would be alpha, right? It would go, because it'd be like a sine wave or whatever, or cosine wave, with a height alpha and a depth alpha, I guess, right? So the amplitude would be alpha.
Yeah.
The only reason that I don't say this is the amplitude, that this statement is the amplitude, is because what if I gave it some velocity too? Then it might go farther, right? If I started at position alpha, but by my initial condition said that I gave it some velocity, it might go a little farther and then back. So the amplitude is not necessarily given by this number.
Oh, so you're saying like there could be more energy put into the system.
Exactly. This is right. This, you could think of this in terms of energy. That's like a good point. In terms of energy, as all the energy here is in potential at time 0, because none of it is in velocity.
Okay.
So therefore, the height that I went to, essentially, I'm calling it height, but it's, the height that I went to is going to be the maximum height, and so of course, you just scale the wave by that amount.
Mm-hmm.
But anyway, this is almost always the initial conditions that you'll see. Maybe you'll have this is something and this is 0. You'll never have both. I mean, what I'm saying is you could, in real life, have that. You could have it, there's nothing wrong with it, just that you'll never give a problem with that, because that's kind of hard.
Problem where they're both 0, or
The problem where they're both non-zero.
Non-zero.
Yeah, but of course, in principle, they could both be anything. And so, let's just do this for now. So we would get, now, of course, to use the initial conditions, we take our general solution, we just plug in the things. So x of 0 is just, well, we plug in, remember the thing in parentheses is t, right? So this is 0, and we get a cosine 0 plus phi. Okay, and this at 0, this is by our problem is given as alpha, and then we take the x dot of 0. Well, now we actually need to take the derivative, so I guess I should have written it here, but whatever. We get minus a omega. Remember, when we take a derivative and then plug something in, we don't plug it in until we're done, right? It's very tempting to be like, oh, it's 0, plug in 0, and then you do, no, it's wrong. So you have to make sure you take the derivative and then plug it in. So one derivative is a omega sine omega t plus phi. The phi doesn't go away or anything. Of course, the phi does not come out because there's no t here, so it doesn't come out of the derivative, but it's still here, so it doesn't go away or anything. But does that make sense? Oh, sorry, dot. X dot of 0. No, I didn't plug in 0 yet. This is x dot of t, and of course, x dot of 0 then would just be, well, plug in t equals 0, and we get minus a omega sine phi. Okay, so now we have two, so this and this, we plugged in our, oh sorry, I didn't say what this is. This is 0. So I plugged in our initial conditions. These two are our initial conditions. Yeah, so if this has to be 0, okay, well, A could be 0, that's possible. But we sort of already know that the amplitude shouldn't be 0 because it started out somewhere. So it's impossible that the answer has A is 0, right? Omega we know is not 0, it's given to us. Or it's not even given. Well, yeah, it is given. It's k over m. It's radical k over m. So sine has to be 0, right? Sine of phi has to be 0. So this equation implies sine of phi has to be 0. Now, in a second, I'll actually give you a better reason of why A can't be 0. Because, of course, again, because we're doing a physics problem, we can think about the system at the same time. But in general, this is a math problem, and there would be no reason you wouldn't want to say that A is 0. But anyway, we'll get to that in a second. But for now, we can use our intuition of that. Of course, A is not 0 because it moved. It was at some position at 0. So anyway, so we get sine of phi is 0. Now this is a equation with solutions. There's actually, of course, infinitely many solutions because what angle has sine of that angle 0? Well, many. One example would be phi is 0. Right? And you actually see that, you know what, we shouldn't say just 0, we should also say pi. And of course, it's also 2 pi, 3 pi, 4 pi, and minus pi, minus 2 pi, right? Those are all true. What you should do is just give all the solutions between 0 and 2 pi, okay? Then we can pick one, but we shouldn't pick one right now, and the reason is because the dynamics are actually slightly, like if we have, like if you plot sine, this is 0 and this is pi, and you can see that it's actually not the same. If you shift it by 2 pi, it's exactly identical. 2 pi and 0 are the exact same thing. But if I do pi, that's actually, it goes down first, and we actually care about that. So we should say there's two solutions, and we don't know which is which yet. And anyway, yeah. So, okay, that's one variable we solved for. The other one was A, and let's use this one. Well, at x equals 0, we have cosine of phi. Well, now remember, we know phi is 0 or pi. And we want A cosine phi to be alpha. Well, of course, cosine of 0 or pi is going to be 1 or minus 1, right? Let's just try 0 for now. So if we plug in 0, we'll get A is alpha. And there you go. Now we're done. Now you might think, well, what happened to this one? We could totally do it. We could say, what if phi was pi? Cosine of pi is minus 1. And then we get A is minus alpha. Or sorry, I should say alpha is minus A, because A is the one we're solving for. Those are actually exactly equivalent. And you can see the minus sign just told us that one place it went down, one place it went up. So we have to like flip it to get it to be the right answer. So these are actually equivalent. But you have to use the same too. You can't mix and match. If we use phi equals 0, we have to use A as alpha. Right? But again, just because like these are waves, they're very symmetric, they have all these symmetries, and if you flip them, they have even more, right? So of course, there might be many solutions, but we're gonna pick one because we have to plug in stuff. So then we'll get x is alpha, so I'm gonna use the first one, alpha cosine omega t plus 0. In general, if you can pick phi equals 0, you probably should, because it's way nicer looking. And of course, if we use this equation for the whole thing, we would have b to solve for it. It would be the same exact thing. We would get the same answer. It would just be a slightly different way to do it. But I want you to see the phi because it's sort of not something perhaps you haven't seen before. So anyway, that was these initial conditions. Now let's actually think about what does that mean. That meant we had a spring at time 0. We started it at some stretched position, let's say. Let's just say A alpha is positive. Of course, it should be the equivalent if it's negative, and we didn't give it any velocity there, so we just sort of let it go there. What happened? Well, we get that the position of the spring is, this is alpha, height alpha, so this is x here, and this is t. And it went just like our cosine. Well, that makes sense. Right? That seems like what it should be. It's a oscillating object, of course, it's cosine, so it's symmetric, so this is minus alpha, right? So now the amplitude is actually alpha. So because we have the solution like this number is the amplitude, which is actually alpha. So if again, I'll just mention that if this was non-zero, our way that we solve for A would not be correct. A here is the amplitude by definition,
Okay.
but A might not be equal to this quantity of the initial condition. Right. Also, they might give you not x at 0, but x at some other time. They're pretty. I would say 100% of the time you'll always see x of 0.
Okay.
Because in physics and in everything, you could just redefine where time 0 is. I mean, it's not like the Big Bang or something. You can choose. So why wouldn't you choose it at 0?
Mhm.
I suppose they could give you different times too. I mean, technically, as we saw, because it's a second order differential equation, you need two initial conditions, and any two, as long as they're not like redundant, should be okay. Like if they told us x at some other time was alpha, that actually we could get a solution. Actually, it wouldn't be unique, but that's a whole other reason. But then let's say they said x at 1 second was also alpha. That could mean that it has a period of 1 second, right? As we saw, the period was 1 second. So that could tell us that it was at 1 alpha, and then it did something and it went back to alpha at time. And that would be enough information for us to do all this again. It would just look a little different. But anyway, almost every time, though, they will give you x of 0 and x prime of 0, because that's and of course, if we just change this, so at time 0, it started at 0 position. Now, if this was 0, 2, it would just, nothing would happen, so it would be boring. But if this was some number, I'll say v naught now, then we could do this whole thing, and I don't want to really do it all out again, but let's just see what would happen. I guess it'd be a little complicated. This would be some number, v naught, and this would be 0. So if this is 0, that means that phi has to be like pi over 2. Let's say it's pi over 2. Okay, and then sine of pi over 2 is like 1. It's not like 1, it is 1. And this was v naught, so that's 1. So then we'd solve for, we'd get a is, minus a is v naught over omega or something. Anyway, I don't want to do it as a whole example, but you can see what, it would be the exact same equations we just solved differently. Or again, if you prefer to use this one because you don't want to worry about the phase thing, you can also do that and you'll get things just like that. Again, when I say that a is v naught over omega, you might worry about the units. So we could check that. That means that the solution I'd get for this initial conditions I've written there would be something like, I'm not promising this is the answer either. I'm just, because I just did it in my head, so I don't know for sure. But v naught over omega, this has units of meters per second, and this has units of 1 over seconds. And so you can see the units of just meters, which is the amplitude. And again, the radians, as I've been saying, the radians don't really count as units, so you don't have to worry about them. So the units still do work that way, but you should make sure that's the case, because a lot of times with these omega squareds and things, it's easy to worry about whether the units work. Actually, we can even check this one if you want. Omega squared is k over m. We solved for that we knew this was a frequency, but we set it equal to some things that we don't have anything to do. They don't have anything to do with frequency, right? Mass and k, that doesn't have anything to do with frequency. So why was I allowed to set them equal? Well, of course, they better be equal because we're using the differential equation like that. But we can see, well, this is 1 over second squared, right? Or radians per second squared. This k is newtons per meter, and m is kilograms. Okay, and now newtons is, it's like newtons is like F, which is like MA. So M times A. But it's newtons per meter, so that's going to cancel, over kilograms, and that's going to cancel, and we get 1 over second squared. So this is not obvious at all. K is a property of a spring, M is a property of objects with mass. They have nothing to do with the frequency, right? But of course, there's a sort of a very specific combination you can do with the units to get frequency, and that just happens to be, it doesn't just happen to be, it's required by mathematics, but it of course gives you the correct things when we, solve the differential equation. So anyway, you should always be able to check units if you'd like. Okay. What was I gonna say? Yeah, we could also use the energy. So we could do this whole thing without solving any differential equations. Without solving any differential equations. With energy, I'll do that. So I'm gonna erase this.
You obviously want us to solve it with a differential.
Yeah, so this is how you get the formula. Now, every time you do a spring problem, you do not have to write this because they all have the same solution, which is this.
Got it.
So you don't obviously have to always do that. I just want to show you because, well, it's in the book, so I assume that he wants you to know. And also, it's very important because, that's where it comes from. But let's say we just want to do with energy. Well, we have to worry about so we know there's kinetic energy. We know how to do that. We have some velocity, which we take the derivative to get the velocity at different times. Nothing in here is constant, by the way. So you can't just, it's not like, I guess that's the same as Moore's energy problems where things aren't constant. So never mind. But the potential energy here is actually kind of different than we've seen before because we're used to like MGH or whatever, right? But in this case we can't do. It's not like MGH comes from mg, which is a force times the distance. We're not just multiplying them though. We're actually doing the integral. It's really work. We're doing this to get the work, which is of course the energy. I'll say potential energy, right? Due to this force is like this. So for mg, for gravity, it's independent of x, and so you just get mgh, right? The vertical component. For this case, though, we have force is minus kx. So u of spring, right, is minus kx times dx, right? Now, the dot product only tells us that they have to be in the same direction. But if this is all a one-dimensional problem, it's just a product. What is this? Well, this is minus, of course, k is independent, and it's just this. This is minus k times, this is x squared over 2, right? So u of the spring is minus kx squared over 2. That's the potential energy for a spring. For some position x, right? If we remember at the beginning, I was saying we could do the whole thing with L, the length of the spring. If we did that, we would just plug in x as L minus L naught, where L naught's a constant. Anyway, you would just basically get this. These are equivalent. This is just if you want to measure the length of the spring as opposed to like the distance from the equilibrium point. X equals 0 always in this equation is the equilibrium point where there's no motion. So if you set it there, it's the natural length. This is if you literally want to measure the length of the spring as compared to its natural length. So again, the L minus L naught is just x, so it's the same thing. But anyway, so this is the energy stored in a compressed or expanded spring. Okay, it's negative because it takes never mind. I'm not going to say anything. Not confusing here. It's the energy went into the spring, and so it's away from the object, and so it's negative. But that's the closest I'm going to get to saying it correctly. Yeah.
Thank you.
That's great.
Barring the fact that I think you've indulged in tautology,
Uh-huh.
I'm not going to say
That's
anything
possible.
that's not confusing.
Okay. Yes.
But
That's not always a tautology for me, but
okay.
yeah. Anyway, go ahead.
Well, mostly I'm just impressed that not everyone understands what a tautology is. So that already made my day. But we're still on 6.2, right?
I just looked at for about a total of 4 seconds at chapter 6, and then I'm doing this.
And that's all it took.
Yeah, he doesn't.
Well, I sort of know the story.
Okay.
I was a driven. Oh, I didn't even.
Dr. Z hasn't gone over this yet.
What are you supposed to read? 6.1.
Through it, but skim 6.3.
Skim 6.3.
I got it right here.
Oh, geez. Okay, I should go a little faster then.
What?
These are so I'm going through 6.1 now, essentially. Yeah,
We're on the same page about that.
Oh, read ahead. Oh, I see. Yeah. Okay. Oh, yeah. He talks about it. So he's doing it with a slightly different notation, but that's fine. Yeah. Okay. Well.
Okay.
All right. I'll talk about driven oscillators in a second then. Because getting into that. Did you?
If the consensus of the table is agreeable to the idea, would it be all right to just go over the answers to 6.1, 2, and 3, and from there go over the
Yeah.
theory behind it?
Are they
So-
in chapter? They're all in 6.1.
They're all in
Well,
6 points.
Yes.
Two,
Oh, they're
6.2. It's in the grid.
Yeah,
Oh,
it's,
okay.
it's all in 6 points. It's all in 6.1.
This is the car one. I got 3.
Okay.
I love this one. Okay.
Is that agreeable though? That we-
Yeah, no, absolutely.
Okay. Anyone go to the party at Fenway last night?
I was at the pub and you guys showed up. John did, but I wasn't there for the party. I was at the House of Blues concert. But it's a long story.
I don't know those party.
Like Lansdowne had like a
I learned about it on
Lansdowne.
like Thursday.
pub,
Oh, okay.
had like a
I see.
like a Halloween party.
If you want to, Keegan, next time an event like that comes our way, we'll shoot you an invite.
Thanks.
You don't think it would be a conflict of interest?
What?
I didn't know until Thursday.
I didn't either. That makes you feel good.
There was a party in my building last night.
Ooh.
In
No.
your
No, I was
apartment
not.
or in
Oh.
your-
In my apartment building. No, not in my.
I thought you
House.
meant like, that's what I
Yeah.
thought you meant.
No.
I thought you were,
No.
hosting.
All right.
No, it was not that crazy. But anyway,
Let me
Here's
know.
what you want to do. You want to climb in through the window for parties like that.
I could climb out of my window. There's a fire escape.
Hey, I'm saying you climb out of your window, you climb into the window of the apartment having the party.
Oh,
You
I
just blend
see.
in,
Right.
and if anyone
think the
spots you,
climbing
they'll
in the
just
window
assume,
might-
they'll just tell them.
Yeah.
Right
Just
on.
blends in. Yeah.
All in on that.
And if they say, "Did you just climb in through the window?" Then you say, "I think you've been drinking too much," and then you move on.
You say it's a Halloween party. Dressed
Yes.
as a
I'm a home invader.
burglar. Yeah.
That's my costume.
Okay, I'm just going to talk about the energy real quick, and then I'll talk about driven, because apparently it's a big thing that driven oscillators, which is actually kind of hard. But they don't seem to be concerned about it, which is bothering me a little bit. But anyway, so if you have let's say it starts at t equals 0 and it's at a maximum position. At a maximum position, there's no, I think one of the questions says you to show this, which, once you have the solution, everything's sort of easy. You can just sort of use this for everything. I just want to give you more of a way to think about it, because this is a little bit hard to, like, one of the questions asks, at a maximum of position, when it's at a, one of these points, or this point, the velocity is 0, well, just, like, find when, set the phase to be 0, because it doesn't matter for this part. Find a time equals 0, time 0 has a maximum position, because if you plug in 0, you get cosine 0 is 1, right? And so you get position is A, which is the max, because cosine is only 1 to minus 1, right? And then if you take the derivative, you get a sine with a t in it, and you plug in that same time, you'll get 0 velocity. So that's just a way you could just literally plug in the same time. The time when you find the time when you get a maximum velocity, plug it into the, maximum position, plug it into the velocity equation, you'll see it has to be 0 because of the difference between cosine and sine.
So, can we do that by graphing, or is there a way to figure?
Yeah, you,
How would we find out that the highest point is the highest point without graphing it?
well, if you're given an explicit, so this doesn't have any, we don't know anything about the height. Well, we do, but it's complicated. But if we just set the phase to be 0, because we're just using an example right now, like this isn't, the phase is for if you have an exact thing, but we can just plug in, we can just say, when it starts, it's going to be, if we just plug in this inertial condition, essentially, this will go away. And we'll get this. This has a highest point. One of them is at t equals 0. Of course, it has infinitely many highest points, but at t equals 0, this has to be t equals 0. There's no, we don't have to choose anything. This is A, which is the max, when t equals 0. And then plug in, you basically want to find x dot of 0, because that's the same time. Find basically you're asking what is this velocity at that point? And of course, because it's the highest point, sort of by definition, the velocity has to be 0, because if it had some velocity, it wouldn't be the highest point anymore. Anyway, but if you just take a derivative, you'll get that there's a sine. Of course, you'll get some other terms and stuff, a minus or whatever, but you'll get a sine of something of omega t, plug in t equals 0 and you'll get that vanishes. So so in this case you'll get that this sine of 0, which is 0, and so you'll get that the velocity is 0 when the thing's at the highest point. Again, that's sort of intuitive anyway. Like you didn't need to really do an equation for that because literally if it had some velocity at the highest point, it would just continue going up and it wouldn't be the highest point. Like it's sort of kind of obvious, but
It's changing. Go ahead.
No, yeah.
It's changing its direction is what you basically said, right? You said what's changing its velocity, so it's got to go past 0, and at the highest point is where it's
yeah,
changing.
sure, yeah, exactly.
Okay.
Because it's going to go negative then.
Okay.
So it has to go to 0. The
Yeah.
velocity is positive and then it goes to negative. Yeah. So,
So the dot over the x is just the derivative.
yeah, sorry. I had those written, I erased them. But yeah.
No, it's fine, it's fine. One dot is one derivative, two dots are two derivatives.
Yes,
The
a
second
time derivative.
A time derivative.
Yeah, if I don't, in the convention is that dots mean time derivatives. Because if I do a prime, now of course if I did x prime, I think everyone would know what you mean. Derivative. But technically, I mean, if you do like y prime, this typically means dy dx, which is not the same as dy dt, right? This because x is usually this is like a slope of something or whatever. But of course, in physics, y and x are both positions, right? So this is you could do this. I mean, this would be just a quantity, but it wouldn't be like a time derivative of some y function. And also in physics, well, you'll never see this because it's like incredibly hard. But you might have both, where you have this and you have an expression that depends like. Well, anyway, you'll never have this, so don't worry. But you could have both theoretically. This would be purposely confusing almost. So you would never do this. But in like I think it's like Einstein notation or Newton notation. This is called. And this is called Leibniz notation.
Leibniz?
In case you, yeah.
Okay.
It's in your book.
Okay.
Oh, yes, it's right here.
Alright, so I understand that when you take the derivative of x position, you have velocity, right? When
Yes.
velocity is equal to 0, that's what we're looking for. But how
Yeah.
do we go ahead and say that, okay, what combination of omega t is equal to 0? I can't quite figure out how we prove that. I know that sine of 0 is 0, but
You know that cosine of 0 is 1.
yes.
And so if you want, so also you know that for an oscillator like this, the maximum position it ever gets to is A. Like you don't even have to use any, like this can only be 1 at a max.
Okay.
So the max this function can be is A.
Okay.
Like ever. So therefore, if I set it equal to A, I'm finding when it's the max, right? This, again, now you could just divide and you get cosine is 1. And therefore, this inner part has to be 0. It has to be 0 or pi or, well, no, pi would be -1. But anyway, 2 pi, right? So these actually have many solutions, of course, but
Okay, so, oh, I see. Because otherwise, if we go ahead and take cosine of any other value, then that means that it's going to be a over 2 or 3 or just a fraction.
it's going to be lower, yeah.
Okay.
We're using the fact that we know that cosine and sine are bounded by 1 and -1, right? And if basically every problem that you'll do, you want to find either when it's 0 or when it's maximum, which is 1. And if you just remember the values, of course, again, there's infinitely many values that it happens, but if you just remember all the values between 0 and 2 pi,
So
they're all going to be 0 or like pi.
So cosine
two.
of 0 is 1.
Mhm. So this
So,
is
no,
1, and so this is A.
No, I get that that's for the second equation, d cosine of omega t plus gamma.
Yeah, that's
Yeah.
the phase. I was using phi, but it's
Okay, I get how that would be 0. But for the first equation, a cosine omega t plus b sine omega 9t, I'm not sure how we'd be able to get 0 for those.
well, so that's not so you would have right, just like with if there was a phi here or a gamma or this, those are equivalent, right? You can't. This is undetermined. There's too many unknowns, so you would have to use the fact that you would have to basically plug in this first initial condition here, because you want it to be in terms of one unknown, because in general this is a solution for every harmonic oscillator. So if they say what's the maximum height of any harmonic oscillator, that doesn't have an answer, because I don't know, I could have a lot of them, right? You have to actually give a specific one. You could do that by plugging in this condition, which just says that, sorry, actually this isn't even the right one. I want like that. Where at 0 time, I want to say that 0 time is when it's at the maximum position, just as an example. You could pick, and usually this is basically this. This will give you a specific harmonic oscillator that does have an answer to all those things. It's specific, but of course you could still have the answers, like, you can't, yeah, anyway.
Okay.
So I just mean, like, this is not enough information here. This statement here does, and this with the phi does not have enough information to tell you anything about the harmonic oscillator because it has way too many unknowns.
Okay. Yeah. Let's move on and get back to this if we have time. Is that
Sure.
all right?
So I just want to talk about energy real quick. So we saw that the energy. So let's say we want to find the velocity at the point. So equivalent to what I was just saying here is the statement that the maximum velocity, right, when the velocity is 1, well, it's not actually going to be 1, it's going to be a omega, but when the velocity is, well, let's just do it. Let's say I'm going to actually solve for the velocity. So again, like I said, once you have the equation, you can kind of do anything. So again, this is a harmonic oscillator that looks like this. This is not a general harmonic oscillator because I required that it starts at this A. It should be really A, but for what I put here. But so this sine omega t. So this is the velocity of the same harmonic oscillator. And if I want to see when is this velocity like maximized, right? Or actually, let's say minimized. Let's say it's at the height, because we know that initially it's going to be a negative value, right? So this is actually going to be -1 right here, or minus something. This is lowest, and the lowest value, remember the lowest this can get, well, this whole thing is in minus. So this would have to be 1, right? So if this is 1, that would give us the smallest velocity, right? The most negative velocity. If this is 1, then the lowest velocity would be minus a omega, right? And of course, that would happen when omega t is, and this would be, when is this going to be 1? The first point is going to be pi over 2, right? And therefore, it's going to happen at t is 1 over omega. I could just do this, I guess. Whatever, this isn't really a helpful way to do it, but you could. It's actually more helpful to say if you plot it versus omega t, and then this would just be pi over 2. But anyway, and now we know that the most negative velocity is going to be minus a omega, which is a negative number, so it's this negative velocity here. And if we plug this in, so this is the time when it happens, plug this into the initial one, we get what? Well, cosine of pi over, so this is omega t is pi over 2. Cosine of pi over 2 is 0. So we get that the position is 0, and of course we knew that happened because we know that when you plot sine waves, the highest slope here, in this case the lowest, it's a little confusing that I keep saying lowest because I just mean the most negative when I say lowest, because anyway, the point where that has the highest slope, right, it's the most negative, is going to be at 0, and that's what we just found right here. Right, so that's equivalent to well, it's not equivalent, but it's similar to the statement I just said, which is that when it's the highest position, it has no velocity. When it's at the max velocity, it has 0 position, right? And same, every point is like that. So that means, well, it doesn't. We could use energy now, I guess, to find it, which is that at here, all the energies so at t equals 0, all the energies in potential energy. We know that looks like this, right? Now, if at this position, of course, x is going to be its maximum value, which is a, right? So we can actually just write this. This is total energy. Because normally when we do energy problems, we say energy here and then energy at a different point. But of course, because there's many points we might choose, we might as well just write that it's the total energy. It's the same. It's the same statement as we always do. I'm just kind of I'm calling it the total energy because at every point, no matter what, it's the total energy. At this point, where's the energy? Well, it's not there's no potential. So kx squared over 2x is 0 here, so it's 0. And then we get plus 1/2 mv squared, right? That's just the velocity. And now let's see what the v is here. So what is v here? Well, these are equal, so therefore the 2's cancel, we get minus ka squared over m is v squared. So therefore v is a, so minus a, it's minus a radical k over m. But we know this is minus a omega, right? This is omega,
Mm-hmm.
and that's exactly
Ah.
that.
Um,
So here, let me just tell you. Here's a math trick for just to keep in your head. It's not a math trick for paper, but it's a math trick to keep in your head that I've been using a lot. That I realize that if you haven't seen it a lot, it's very confusing. The trick is that, and it sounds kind of obvious when I say it, but it's very useful. Is that cosine and sine are bounded by 1 and minus 1 always. So the coefficient, I just sort of treat as its own thing. Like I basically, when I say, when is this maximized, I just want to say, basically, it's this value. So because cosine and sine have this, it's basically a convenience. The cosine and sine have this convenient feature that the maximum value is 1, and so whatever the coefficient is sort of the value that I care about. So in this case, what is the maximum velocity? Well, it's just the coefficient of my velocity equation, because this is bounded by 1 or minus 1. And again, the sign doesn't really matter. If I got the wrong sign, it would probably just be because I did the wrong, but everything's sort of symmetric, so it doesn't really matter. But I mean, you should be careful. But in this case, keep track of the fact that we did get a minus sign here, and that might seem a little weird, but then when we plot it, we see that it's down, so of course it's a minus sign. If we did the same exact thing, but we did the next part when it's going up, we should get the same formula. We would get, we'd plug in a different t, we'd get 3 pi over 2, and this would be minus 1, and therefore we'd get plus, everything would work out the same, of course. And then also, so I should mention that too. Because we took a square root here, technically it's plus or minus, right? So technically, we get that, right? Now, actually, well, okay, all right. Yeah, it's technically plus or minus because we took a square root here, so that's plus or minus that value. And that makes perfect sense because this equation, if we did this exact same thing, but for this point, what should we get? Well, we should get the same velocity, but it should be positive now. But this would look exactly the same. We wouldn't put any signs or anything here. If we were using point 1 here, which is this point, and point 2 here, which is this point, we got the correct solution. But if we're using point 3, that's fine. This is exactly the same thing we'd write. So how do we know if it's positive or negative? Well, because of we took the square root of the velocity. So and all of this is actually a thing in energy formulas that people, it doesn't really mess you up that often, but it's important to remember, which is that it always has the velocity squared, which means it can't, by definition, it cannot tell you the direction of velocity. So in every kinematics problem, we just sort of know the velocity, like it's a roller coaster, and it's like, well, it's not going backwards. But technically, it could, like you could have a roller coaster with some problem, and then it could go up, and then it could go backwards, and we'd have the same exact equation. And the reason is because when we found the velocity, we had to take a square root, we get a plus or minus, and we get that it could have been going backwards. Of course, in real life, in physics, we put the signs in sometimes based on our own intuition of the problem. We kind of know what's going to happen. So anyway, okay, does that make sense? So this is energy. This is basically the way you do every energy problem in here. It's the same as the potential, like mgh and 1/2 mv squared, except we use this for potential now. It's not always a here, it's x in general, because, right? So if we're using like for a point halfway or whatever, it generally would be very hard. Because if we're using a point halfway, like this is point 1 and this is I'll call this point 4, all the energy is, so we know the total energy, which is this. The total energy then would be then at this point, at point 4, will be minus kx, I'll say x of 4 squared over 2. X of 4 just means the height. So this is x of 4, this height here. Plus 1/2 mv of 4 squared. V of 4 is the velocity at this point. But of course, now we have too many unknowns here. So, but these are related by this, and you can see how it gets a little complicated. We would get like a cosine squared, sine squared type thing. So I'm not going to do it again because from here to the answer is sort of just algebra, which you probably can't see in your head because it's very complicated. But I assure you that there's some I can't see it in my head, but there is some way because I can tell that of course this x squared is going to be this squared, which has cosine squared. This is going to be sine squared, and you'll get something that cancels and looks nice. I'm not doing this because I don't think you'll have a real problem like this, but you can see that of course this is just what we already know, which is that if we know the total energy, which we can just pick a point when it's at, just like in an energy problem, we pick a nice point when all the energy's in, MGH or whatever. Same thing, we pick a nice point, that's the total energy, every point has that same energy. Usually we'd pick another point that it's all in another place, but we could pick one that it's in some in each. And that would just be, we know the two expressions, we could just do it. And because the v and x are related, that makes these solvable. Whereas in other kinematics problems, they might not be solvable. So anyway, yeah.
Alright, so for the previous problems, the idea was that, okay, we've got a free body diagram, let's map out the forces on the free body diagram. After that, okay, let's make some formulas that relate these guys to each other and set them equal to each other, because there's an equal and opposite reaction to everything. And that's generally the starting point. What's the starting point for problems like these?
Sorry. Well, okay. The starting point is that you have an object that has a force on it, one force on it. Okay. It's only one force. There's no balance or anything like that, and the force looks like this. And we were talking about how this is sort of complicated, but it's not. It's not just one example of many that give random things, and we're just picking one for no reason. If we put like a plus sign, that would mean that we have a force that pushes you away from the origin, right? The force goes in the same direction as the displacement. That would mean like if you're on like a little hill and you just rolled away. That would not be very interesting. If we had something, well, you could go through some examples. If we had something more, if we had v, that would be interesting. We just did that with the drag thing. It was v squared, but it would be very similar if it was v. So we've kind of already done that. And actually, in like 30 seconds, we'll talk about if there's a v term too. If it's x, though, that's sort of an interesting example and gives you interesting dynamics. That's why we're doing it. The other ones are sort of not interesting. But this just means, yeah, if you have it's kind of like being at the bottom of a hill. If you go in one direction, gravity is going to push you back toward the center. Now, in this case, this is called Hooke's law, and they basically only ever talk about this as a spring. Now, a spring, in terms of energy, has the exact same properties as like a hill. But it's a hill that's shaped like a parabola. So it's a little, that's why they don't do that. But a hill that was shaped like a parabola, like exactly a parabola, would have identical dynamics to a spring with that force on it. And you could see, I mean, it would be a little, well, yeah, you could see because then the height, it would be like mgh for the energy, but the height would be related to, if this is x squared, the height would be like x squared, and you'd have something like this. Anyway, I'm not going to go over the whole thing because that would be a silly example. But you'll see in quantum mechanics, when I talk about harmonic oscillators, they're 100% of the time talking about a potential, which we'll talk about why that is in another time, but a potential that's shaped like this. So a potential shaped like this is exactly equivalent to a force like that, minus x something, right?
So what's the step after? Okay, so we have a force. It's harmonic oscillation type problem. We have one force acting on it, right?
Okay, I don't say anything about harmonic oscillator yet. We don't know anything about it yet. We just know that it has this. If you were starting from the beginning,
Okay,
then
from the beginning.
then F is ma. That's just always true.
Okay.
We know the forces are not balanced, so we don't have to like set things to zero or anything. So ma equals this. A and x are related by derivatives, right? Acceleration is the second derivative of x. So if we plug that in, this is a differential equation, and this is the solution. Well, this is the solution, or this.
Okay.
So that's how we get to this. And then this has two unknowns, a and phi, or a and b, which makes sense because it's a second order equation. And to solve them, we would have to plug in some initial conditions because, again, like I said, this gives you every harmonic oscillator. That's not enough information to tell you about a specific harmonic oscillator, which a specific one is where you know the height or whatever the velocities are. So to get that, we'd have to plug in two initial conditions. Usually it's the position at zero. Position at time zero. So where is it at time zero, and what's the velocity at time zero? They could theoretically give you any velocities, the velocity at any time and the position at any time, and it should be solvable, but that'd be really mean. They really should just give you the position and velocity at time 0. And based on that, we could solve for these two and get the explicit expression of the oscillator. We could read off things like, we just take a derivative, we could read off things like the velocity at different times. We could set them to be a value we want. When is the position 0? We could set that equal 0 and solve for it. You can't solve for it in general easily because there's way too many things, as I said. But yeah.
Okay. So what I'm getting from all that is that at this particular point in time, we can make the assumption that the object has a force acting on it, and that force can be expressed as negative kx, k being a spring constant, right? A coefficient.
Yeah.
Okay.
It's
From there, we found a relationship between x, distance, the mass, and the coefficients.
Mhm.
From there, we can say, okay, the answer is definitely going to fit in that function, a cosine of omega t
Yeah.
plus gamma. All right. In which case, the maximum value will be when cosine is equal to 1, in which case the maximum value could just be the coefficient a. And
Yes.
That's pretty much everything that we're at right now.
Yes.
That's the starting point.
Yes, right. The reason that this is the solution, though, is because if you plug it in, you will get that this is true. You can't just pick any. It's not like I'm telling you you have to believe me. You don't have to believe me. But this is actually the solution because if you plug it in, you'll get the answer. You actually only get the answer, of course, if omega is square root of k over m.
Okay.
So you'd have to, figure that out. So.
Here's my big area of concern.
Uh-huh.
If it's really that easy, then Professor Z would not have made this the subject of a homework problem. He wouldn't have asked us to read ahead. So
I don't believe you. He would totally make it a homework problem because it is that easy.
No, but it's like how can he trip us up on this? Like where's the catch-22?
Wait a second. Well, first of all, this can be a little tricky, right? I've given you the most general thing. So actually, it's not that tricky compared to other problems that you've already done, right?
Yeah, compared to quantum mechanics. I'm not sure
Well,
that-
you'll see. No, but don't think that because something seems too easy that he can't give you a problem on it.
No, I agree.
In the
I'm just
homework,
asking-
'cause
I'm
it's-
just asking, how do you ruin a perfectly simple thing like
We
this? and
will-
introduce-
I'm gonna write something here. So
I'm just here to screw up your day.
M.
Do you think this chair has seatbelts? Buckle up. Buckle
There
up.
you go.
Okay, now I'm gonna ruin it. So let's say instead of as I was saying, let's just deform it a little bit. This is called a damped. So the other one was called a harmonic oscillator, a free harmonic oscillator. This is called a damped harmonic oscillator. So I'm gonna and what was it? A driven. And of course, you could have a damped driven.
Those get
Oh.
I remember
ruthless.
this.
Now, of course, that's actually not going to be more. It's going to be more complicated because there's two things, but it's not going to be more like. Well, you'll see. I'll get to it. But if we add this is called the damping force. You've already seen these damping forces. Now, this is not the one where it's like a block hitting air, right? We've seen we did that, and that has a v squared. This is just, and then the reason we don't want to use dv squared is because it actually gets incredibly complicated. It's easy. Well, it's relatively easy in a straightforward like kinematics. There's some drag force.
Mhm.
This is slightly different. This is just with a v dependence. It doesn't really matter that much. For small velocities, it doesn't really matter. And this could be like a good example of this is like a spring with a block underwater, right? Could be in air too. In underwater, it's still, you're doing the pushing the things away, and it should be v squared. But you can say it's going slow enough that we'll just use v. It's a Taylor expansion, right? Or it's like a block. You could have like a block. Okay, this is not a good example. But let's say you had a block on a spring horizontally, and it was going on like sandpaper, right? Now that's based on what we know. We should use mu times the normal force, which is constant. This is not dependent on velocity. So that's why I said it's not a good example. They literally just use whatever damping force. Damping forces are so weird that they just use whatever one makes the problem easier. So is this really the right damping force? Sure, why not? So we're just using. Now, you can see that it actually makes it easier than if we used v squared, because this, now the equation becomes this is just ma I'm plugging in. This, we get a term that looks like b times x dot, right? This is x dot. Now, if we had v squared, we would have x dot squared. Now, and this wouldn't be a linear differential equation. So remember all the names of all the different, I don't know if you've seen like a list of them somewhere, but there's like names of, well, there's not names of all of them, but there's names of ones that are solvable. And this is called a linear differential equation because every derivative is not raised to any power, right? You could have, you know, higher power derivatives, but it's not like we have it's not like we have, I should write this as x double dot. It's the same thing, of course, I'm just keeping it consistent, but it's not like we have x double dot squared. If we had anything squared, it would not be linear anymore, and it would be have a completely different type of, we'd have to use different methods to solve it. This is a linear differential equation. To solve it, we could, and they actually don't even do it in the book I was just seeing, they literally say, using the complex exponential form, I'm just going to copy it because they just give it to you. So to solve this, you could, again, well, okay. I'm trying to show you how to solve these, but technically there's literally an entire class you'd have to take to solve all these. So at some point I can't, as much as I know you would love to see how to solve every possible differential equation.
That's why I came here.
Oh, it's fun. And what are they? So, psi, gamma. And gamma is,
Why am I writing this down?
oh, it's in the book. Sorry.
I know.
I'm copying, yeah, this
No,
is
I
in
was
the book.
talking
So
to myself.
this is on, I'll say this for the video. It's on page 91. M gamma. It doesn't, these are just letters. I don't know why he wrote B. It's usually B, but they use. Anyway, you basically get, wait, sorry. What is delta? Oh, he said in the, so he said in the thing that delta and gamma are the same.
You really don't like
That's-
that textbook, do you?
No, I really don't. Oh, because he used, I see. So this should be delta. Okay,
No.
it's the same thing.
Alright.
And also then he used gamma before for something else, but it's the same. The phase is just some angle, you know, for this, right? If you plug, so remember how I said at the very beginning that we could actually get this equation. I knew this was the answer because sine and cosine have the property that the second derivative is minus of the function. But we could use e to the something because the second derivative is still proportional. But to get the minus sign on the second derivative, we'd have to use an I in the exponent. And we could do the whole thing with an e to the I, but of course then we have to plug in the Euler formula, right? And we get this again. So that's fine. Now, because we have another term, we actually can't use, so cosine and sine do not solve this at all, right? So we cannot use cosine and sine. We actually have to use the complex form. This is the example solution. This has unknowns. This is not an unknown because we could solve for it, but if you just plug this in here, we should be able to get, you would get an omega squared plus, yeah, omega squared. I think that would be fine. Yeah, this should be good. If you just literally plug this in here, right, it's first derivative and second derivative, and you use this is just an abbreviation. This is not a, we're not solving for anything here. We're just defining this quantity to be this, and then it would work. We get this. So instead of this as our simple, free simple harmonic oscillator, this is our damped harmonic oscillator. The only, oh, okay, that's fine. Yeah, yeah. Now, we can actually write this in a little more, you know what? I don't believe that. Okay, this is question 3. Okay, question 2 we kind of just did. Question 1, we also did at the beginning. It's just finding, yeah, it's just, question 1 is just finding the relation between these two, which you could, if you draw a graph, it should be, you could choose some mathematics behind it. Oh, I see. Wait. Oh, I see. Okay. So yes, they're right. I believe them now. So what this is incomprehensible. Okay, let's try to write it. So I'm going to erase this now. So this exponential here doesn't mean anything if we just read it. It's like, all right, great, it's this. Let's actually plug in this and just see what we get. Okay, never mind. It's not going to be nice. Wait, what is this? Did I copy this wrong or did they say it wrong? Okay. Okay. Hold on a second. Something's wrong here because they literally say this. This doesn't make any sense. Okay. Anyway, so I'm going to use something below. So these are going to be roughly. So this is not right, but it's going to be something like e to the I minus gamma squared over 4 plus I gamma over 2. Okay, so that's omega. So this should be omega plus delta. Okay. So if I were you, they tell you the solution. Well, okay. I'll show you how to. So this is how you get equation 6.6. That's what I'm going to say. This is how you get equation 6.6 from 6.4, I guess. 6.5 I don't believe is correct.
Oh boy.
So anyway, I'll tell you what to Google in a second to get a really good explanation of this. So let's see, what is this? Well, this is some complicated thing. Gamma has to do with the damping force. Now the reason you could, of course, B is just a coefficient. You could just write it in terms of m times something. The reason they want to write it in terms of m times something is so you can divide everything by m. Remember in the last one, if you just divide everything by m, in the last one we had k over m was very important. So they're just defining b over m to be gamma. So that's what gamma is, so you know. They're all just positive numbers. K over m this is omega. Omega naught, I think, and I believe this is omega. This is what they want to say. What they want to say is that there's an omega here, it has the same form as the previous one, but omega is now squared, is now omega naught, which is this, plus something with gamma in it. It's not gamma, but it's like, I guess it's gamma squared over 4 or something. Something like this.
So that's what omega squared should be?
I believe. I'm not guaranteeing that the coefficient is right, but it's omega. Squared. I believe what they want to say is omega naught. They want to use omega naught to be what the omega naught was in the previous problem. It's always just k over m, right? But of course, omega, the frequency is actually going to be slightly less than that. So let's probably do this. Okay, let's pretend this is, and I'll show you why it's. So again, the intuition is actually not that complicated here. It's just that the equations are. And now let's write what this is. With this here, we get e to the I times something. I'll set gamma delta equals 0. Let's just say it starts at, like the previous problem, it starts at maximum position. So we get this. Now notice there's two i's here. That comes from the fact that when you take a square root of this, it's a negative number, and so it's actually complicated to take a square root of this, but you get something with an I in it. And there's an I here because the whole thing was in complex exponentials. So these actually become, I'll write it as a separate exponential. It's actually a minus gamma over 2. And now e to the I something, again, I'm not telling you what this is because I don't know, but it's something like this. E to the I something is something like a cosine, omega t, okay? Then you get e to the minus gamma over 2. Now this is not a complex exponential, so we cannot write this as a cosine or sine. This is a real exponential. What does this real exponential look like? What do e to the minus something positive is what? It looks like that. it's a decaying thing, right? Because if you just set omega to be 1 and then 5 and then 10, it's a lower and lower number because it's e to the minus that number, right? So this component, this is e to the minus gamma over 2. And of course, well, okay, it's e to the minus gamma over 2. And of course, it crosses 1. Of course, you could set it would be 1 at 0. But anyway, it doesn't really matter. Then you get, so this function times this oscillating function, this is just a oscillating thing. Now, the amplitude seems like it would be, the amplitude of this cosine is whatever the coefficient is, remember I said? Because it's just the cosine can be maximum 1. So if the coefficient is d e to the minus gamma over 2, that means that this cosine oscillates with an amplitude equal to this function, right? Does that make sense? And of course, because it can be negative 1, it's also bounded by the negative side. So if I write d e to the gamma over 2, that's like this, minus, this is going to sound weird. It seems like I'm going a little too far, but I'll explain why. This is minus d. This function here is minus d e to the minus gamma over 2. And this just says that you have an oscillating function with an amplitude bounded, the amplitude bounds it, right? Bounded by this function. So that looks like this. And of course, because these functions go to 0, this will eventually go to 0. So a way you can think of this, so this is you could think of this as, this is some complicated function that I can just graph, okay? I guess that's fine. I think a really helpful way to think of it is, like I said before, whenever you have a cosine, you know it can be 1 to minus 1. It goes from 1 to minus 1, and the amplitude is, the amplitude is whatever the coefficient is. The coefficient is actually d e to the minus gamma over 2. I can plot this, and then I know that cosine must have an amplitude that's dependent on that thing. Of course, if that thing shrinks as you get higher and higher in t, sorry, there's t's everywhere, whatever. Because you have to graph it over t, so of course there's t. So as you get higher and higher in t, you're going to get a narrower and narrower coefficient of your cosine. It's still going to oscillate. This doesn't care about anything else. It's just going to oscillate all the time. But as you go, right, now let's look at this. What is this actually equal to? Now, I didn't draw it in the right starting position, but it should really start up here at time 0, but whatever. This is something that's oscillating and dying down. That's literally what we started with, a damped harmonic oscillator. It's a harmonic oscillator, but its amplitude is decreasing, and then eventually it's going to go to 0. Of course, it's never actually going to be 0, because this coefficient is never going to be 0, but in real life, of course, you can say eventually it sort of dies away. Sorry, it's confusing that I've written the word driven harmonic oscillator. It's not driven. This is a damped harmonic oscillator. Okay, does that make sense? The complicated parts were the middle parts here, and these are things you should look up. So you should go on, I know this, I say the same two places because they're actually really good. If you go on Paul's online math notes.
Oh yeah, I love that guy.
Or just Google, if you just Google damped harmonic oscillator, make sure it's not driven, but if you Google damped harmonic oscillator, you should be able to find someone that goes through all this. It probably looks almost exactly like what I've written, but there's just some minor details. It appears from the book that you have no obligation to know any of them, because he doesn't even seem to know them. But, well, he does, but it's just, there's a kind of major misprint. And the point is, though, that actually here's another subtle point that's actually a little confusing. This omega is not omega naught. It's actually omega naught minus something. So that's definitely true. If you want to, basically what he's saying is, if you use the same test function, this is the same exact test function as the one we had. It's just in exponential form now. This is the same test function. If we had no damping force, we would just have omega naught t, and we get cosine time when we just did. In this case, we actually get, if we try to use the same form, we get that omega squared is not just k over m. It's it's k over m, which I'm defining to be a variable called omega squared. That basically omega naught squared. Essentially, they're saying that omega naught is the one, if there was no damping force, that's what it would be. But anyway, minus this other thing. And this other thing comes from the damping force, but that means that this is like an oscillator, but the frequency is actually a little slower, right? A little bit slower than what it would be without the damping. What that means is that, like, the time between here and here, this is actually, well, now we get into the confusing part where omega is 2 pi f, right? And the period, which is the time between here, is 1 over f, which is 1 over 2 pi f. Oh, sorry. That's not what I mean to say. The period is 2 pi over f. 2 pi over omega, sorry. Okay. And now, so this is the period. So in terms of omega, that's saying that this period here is a little longer. Yeah, right. Sorry, I confused myself. It's a little longer because the frequency is lower, right? If you have a lower frequency, it's slightly lower. Now, of course, gamma squared is probably going to be small. I guess there's no way you'd really know that, but it is. I promise. It's going to be very small, and so this is going to be very close to omega naught, but slightly less. Therefore, the time, the period between each, identical points in the oscillation is going to be a little longer, and that kind of makes sense because it's kind of like saying if you put some friction on, not only is it going to die down, but it's actually going to not quite do the full revolution at the same time because it's sort of being slowed down. And it's not slowed down by that much. It's much more apparent that it's damped. So if you plot like the omega naught, it's probably not that much different, but it's slightly different because of this effect. So when you add, so here's the summary. When you add a damped part to the oscillator, you get one new term, but you actually get two new effects that make it different from an undamped oscillator. The two new effects are, one is you get an extra term. So the setup is you try the same exact formula as you did before, but of course you leave it as a complex thing because if you plug in sine, it doesn't work. It does still work with this. You just have to set omega to be this. I guess I could just do it. It's not that hard. Well, anyway, if you just literally plug in this formula to here, you should be able to figure out what it is. It's like, there might not be a 4 then. Maybe I'm forgetting something. I think there's no 4 here. Anyway, whatever. And so you just get this, and that's fine. Now this is your answer, but of course, to actually find the dynamics, we're going to need to plug it in, plug in omega. And of course, in here we need the square root of this thing. And the square root gives you two terms. One of them, this one, just lowers your frequency by some amount, right? This one just says that instead of radical k over m to be my frequency, my frequency is now k over m minus some amount. There's got to be a 4. I don't know where the 4 comes from. It comes from somewhere. Anyway, whatever. And so that means that my frequency is slightly slowed by the damping. But the more major effect is the second term, which, as we saw, because it's a complex exponential, because there's an I there from the minus and the square root thing, we get a completely separate non-imaginary term. This is not oscillating. It's just damping. And we get, therefore, that the oscillation part, because there is still an oscillation part. It's not like this went away. This could go away at some point. You could have I'll talk about that in a second. You get a damping part bounding the oscillating part. So the oscillating part still continues, but you get that its magnitude, its amplitude, I should say, is decreasing over time. Amplitude, again, is the coefficient, the thing multiplied by cosine, which is d times this. This is decreasing. This is bounded by 1 and minus 1, so if you just plot plus and minus of this, you get that the cosine sort of bounces between them, in those two functions. The two functions are a plus and minus version of this. So again, it's using a little trick of cosine. The top of the cosine should be 1, and the bottom should be minus 1. So therefore, if I multiply by something, the top should be this, and the bottom should be minus of this. I was going to say, though, what if this completely went away? As I said, there's two pieces. There's an oscillating piece and a damping piece. What if somehow I turned this up so high, turned this gamma up so high, that this was 0, and I still had this damping piece? What would that look like? Well, that's possible.
Is that overdamped?
Yeah, it would be overdamped, which means that, let's just say it's actually 0. Now, technically overdamped, I think, would mean that it's sufficiently high. It's complicated. I don't remember
I
what
just
it
know
is.
it travels to 0 quickly, and you
Yes.
can't record it.
Exactly. So that means that, let's say this goes to 0, and we just get this. We just get this term. Now it's still, sorry, that's not D, it's D times this is X or whatever, right? That would just look like that, right? There's no, now you could have, the reason I was being careful is because if this was very, very small, you could have a very slow oscillation times this, such that it goes like that or something. Like it could do something kind of complicated, right?
Oh, yeah.
But it would basically, I think overdamp just means it doesn't do a full oscillation or something like that. I don't know.
Yeah, that's what I was. Okay, so you drew those two. The second
Yeah.
one you drew. Does it actually go past equilibrium?
Oh, I'm just saying. So there is a set of values for. There is a value for gamma, such that this is the solution.
Yep.
Whether you call this overdamped, I don't know. Actually, you might not call it overdamped because it does oscillate. Yeah, you're right. So
it's not.
I think what you're probably right, which is that if it's overdamped, it doesn't
It
cross
doesn't,
it. Yeah, you're probably right.
it doesn't go past equilibrium.
Yeah,
it just
sure.
goes to.
Right, basically overdamped qualitatively. If you're actually using it, yeah, you probably know what it means better than me. But qualitatively, I think of it as just the oscillation part is so non-significant that it's basically like a thing that's just going to equilibrium. Like if you had, a really weak spring that sort of bounced back and forth, but you put it underwater, and like it doesn't have enough sort of power. I shouldn't use that word because that's a physics word, but doesn't have enough juice or whatever to like.
Potential?
Well, no,
Again, yeah.
it still is. Well, okay, you could think of it as energy. Yeah, it doesn't have enough energy to like push all the water out of the way, whatever. Anyway, basically, it looks like it's just something going to 0. It doesn't look like something oscillating at all.
Right.
And you could imagine, yeah, if you just made the oscillating part weaker, right, the K weaker and the D higher, that would essentially give you, it would kind of stretch this out this way.
Yeah.
So it would make this longer, and it would sort of crunch you. So you might not even really see the oscillations. Anyway, so that's overdamped. Underdamped is just this. And then there's a thing called, critically damped is when like they
Oh,
balance each other or something.
that critically damped might be the one where it doesn't go past.
Yeah, or just barely or something goes to 0. Like it. Anyway, there's
It's-
words that are not.
That might have been the one that you can't measure.
Yeah, perhaps.
I don't remember.
Anyway,
Yeah.
Everyone's free to look this up if they'd like. It's definitely in a math textbook. I don't believe you'll ever need to use this. Well, you
Does
might
Khan
need to use
Academy
this, but
have an explanation of it?
yeah, there's some. There'll be probably a video or GIF that's better than my drawings here.
Okay.
So that's anyway. So those are damped oscillators. Okay. Now, let me just, and I don't mean to like fly through anything, but I do want to like just, because I'm not going to talk about it.
6.4 is a throwaway.
6.4.
It's basically asking us to define what
There's
omega,
only,
gamma, and delta are in a function.
question 6.4.
It's a throwaway.
Oh. Yeah, okay.
I have a few questions about taking the derivatives for 6.2 and deriving 6.3 though.
Yeah, sure. Well, let me just quickly say,
No problem. Take your time.
let me just quickly say a driven oscillator, because I'm not going to do a whole example because it's really hard.
You can be dressing up as anything for Halloween, Keegan.
A driven oscillator, yes. No,
You get a leather jacket,
Yeah.
a baseball bat, you'd be pretty well off. You'd be
I
Negan
could.
instead of Keegan.
Wait.
Sorry, what?
No, you know Negan from The Walking Dead?
Oh.
You get
No,
a leather jacket and a
Oh,
baseball bat.
no, I don't. I knew there was a character named that, but that's funny.
I mean, you already got most of the
Didn't he
costume
like
already.
kill some major character or something? Spoiler.
You
That's
say
what I
spoiler.
heard. Hmm.
You say spoiler before you give away the details, but yes.
Okay.
Mm.
Like he killed like half the ethnic diversity on that team. It was
Ah.
nuts.
Is it over yet?
I don't know, honestly.
I kind of hope it's over.
Somebody was
My roommate in college liked it, and I didn't like him. So anyway, no, my one roommate, my next roommate, really was a nice guy. But
At this point, the show itself has become a zombie. It
that's
just-
true, exactly.
And therein
Just
lies
want
the
to
beauty
be.
of the production.
Yes, they got us good.
Mm.
Okay. I mean, I would say, sorry, I'm making marks on your book.
Whoever had it before me. Yeah, it's damaged.
Okay, the book is not really telling you anything about this. Basically, a driven oscillator has another force, so the net, this is really the net force, which we're going to set equal to ma, has another force, plus F naught, which has something like this. Now this, e to the minus I omega t, remember this is just like cosine and sine. This, though, omega is completely separate from any of the omegas here, okay? So all I've done, this is not like, I don't want to make this seem like a completely different thing. All I've done is just say, I started with, what is my net force? It's just the spring force. F is ma, and then we get this differential equation. Then I said, what if I have two forces, the spring force and the damping force,
So it's
set
very
equal to ma,
damped.
I get a different equation. Then I said, what if I have three forces, a spring force, a damping force, and another just separate, called a driving force, which is oscillating. Now, of course, if I just put a constant, it wouldn't be very interesting, because it would, anyway, you could do a differential equation for that, and it wouldn't be very interesting. It would give you like a shift in the
So
equilibrium.
you're just adding force initially.
I'm adding, this is constant force, though.
Yes.
So this is an oscillating force, which means that you have, like, it's kind of like you have
I think of the spring on a motor. I've seen that.
yeah, exactly. It's a spring that has a block on it that has friction.
Yeah.
But you're actually like shaking the base of the spring,
Yes.
right? So the thing doesn't have to necessarily respond. It's not like this thing goes with the spring. That would be sort of boring. It could for some limits of when the mass is very small or whatever, right? But it will basically the reason they write it like this. That's why I'm writing this. You could write it with cosine, right? You could put cosine omega t if you want. Whatever. The point is that you get F is still ma always, obviously, since 1607 or something. And that's equal to this plus, and then we get a plus. I'm not going to write everything, but you get plus this, and you get a differential equation with this. Now this is not dependent on x or any x variable. This is dependent on t though. So that's what makes it solvable. So if you put like an x here or whatever, it might be impossible. So the reason that we can solve it though is because this is called I think it's called a homogeneous. No, it's not a homogeneous. Anyway, there's another word that you add. So now this is called like a linear, second order, non-homogeneous, ordinary differential
Does
equation.
this help you find the harmonic frequencies?
Yes, because so the reason this is important, the reason this is interesting, I should say, is because this omega here is completely unrelated to the omegas we've been talking about. The omegas we've been talking about are a property of the system. They have to do with the block. I mean, we saw it. They have to do with the block, the spring, and the whatever the damping coefficient is, right? These have to do with the system. This is like the natural frequency, I would call it. I don't know if they call it that in the book. I've heard people call it that. This omega naught is like, or in this case, this omega whole thing is called like the natural frequency, okay? If we add a driving force, now it's possible the whole thing could oscillate at close to omega, the driving frequency, but it doesn't have to, right? You could imagine like, something goes like this, right?
Mhm.
Then it would, I guess that's the same frequency. Anyway, you can imagine something really complicated. Like if you're oscillating too fast and it can't quite respond and it sort of does some complicated motion. It might even have some complicated motion like, like that, right? It might do some, right, it could do something really weird.
You could just cancel out the force too.
It could actually right, it could, well, I would say it could probably only completely cancel out the force if the mass was very large.
Isn't it like the same frequency but at the exact opposite phase?
That's a possibility, but that's not necessarily true.
Okay.
That would be like if it was going like this.
Yeah,
So there's things called normal modes. Is what you're talking about?
it might be.
Okay.
Yeah,
There's-
I'm trying to remember it as I go.
There's a whole so in the class probably
Yeah.
they spent very little time probably talking about all this and probably a long time talking about normal modes,
Yeah.
which is things that I don't think we're going to do in this class. But basically, when you have a driving force and a driving frequency and a natural frequency, you can, instead of expressing it as a very complicated, we all saw how complicated it can get already without a driving force. But instead of expressing it like that, you can actually express it as there's two ways it can move. It can move like this, and it can move like this. And actually, you can express it very simply in terms of that. They don't talk about that in the book, so I'm not going to talk about it. I would like to, because that's much more interesting than any of this. But I would say, yeah, just like, so equation 6.8 kind of tells you so it's essentially the same solution. So 6.8 tells you that it's essentially this equation, but D is now what 6.8 says, which is D has something like I don't know, I'm making this up, but it's something like this. This is D. In other words, D is dependent on both frequencies. So therefore, if you get something else complicated, anyway, I don't want to talk about it. It's not really going to be. They don't show you how to solve it. So it's just the point is that there's much more dependence, and you get some things called resonance, which is when it might be a minus sign actually. Yeah, it is
Well,
minus. It's actually I think the minus goes the other place, but it doesn't really matter. The point is that when these are similar, you get a very here's actually I'll say this is the last thing I'll say about this because I don't want to talk about this if you're never going to use it. But the point of resonance is that this is the amplitude, right? If omega naught and omega, that means that the natural frequency that it wants to oscillate at by itself and the driving frequency are very similar. They're equal. This goes to 0, and you get 1 over. That means that D, your amplitude, becomes larger.
It just grows.
It goes
Yeah.
a lot. And now, if there was no
Exponentially.
damping force, this would be this would grow to infinity. That means that if you have an exactly resonant system, if you drive it at exactly the frequency it wants to oscillate at, and there's no damping, it technically grows to infinity, right? The amplitude goes to infinity. As you tune the drive, let's say you can, because you can't tune this one, because it's just based on K and M and all that stuff. But if you can tune this one, as you approach the natural frequency, you will oscillate to infinity. Of course, every system has some damping force. So eventually you'll get to a point where its amplitude is actually just very large. It's not infinity, of course. But in ideal systems, we could say that there's no damping at all, and
The example you gave that I remember was like the pistons of an engine.
Yeah.
And how they're designed to not idle at or near a natural frequency at
Yes.
all, or even shift near one.
yeah,
So that was kind of interesting, and
Yeah.
he showed like an example, like a video I forget, but of something like that spring
right.
where they added a natural frequency and the thing just shook and broke.
Exactly. Yes. Right. Like earthquakes and stuff. They try to
Yeah,
make
yeah.
the buildings. Of course, because there's many systems in there's many things welded together and stuff. They have many natural frequencies. Like this has one natural frequency, but like this has another one depending on the right. So you have to make sure. So actually really tall buildings, have really really low natural frequencies, and actually they're much safer from earthquakes. So and of course really short buildings have very high, basically middle height buildings. I don't know what middle height means. I don't remember, but I saw it somewhere. Yeah.
Yeah, that was a good
Middle
one.
I was
height
just about to
buildings.
say, yeah, yeah.
It's a simpler.
Yeah.
Right. Yeah, and that's
why
the wind is
Yeah, that's why we want a bunch of different frequencies when you're building something.
exactly right. If you have just one, of course, if you
Seen-
have just one, that's okay if nothing's going to hit it with that frequency. But earthquakes have a range of frequencies that just happen to be sort of like the resonant frequencies of some middle buildings.
Yeah, they're gonna get it out eventually.
Right.
Have you seen the video?
And you
is
could
this
put
the video
stuff
where
in
the
it.
cat's walking across the bridge?
No.
Apparently, they walk at the perfect frequency to make the bridge go haywire. Look it
funny.
up. It's like
Those
cats
cats really-
walking across a bridge.
Those
Will
cats really are evil, aren't they?
yeah, they are.
Oh.
No,
Yeah, they walk at the
That's-
right
that's
pattern,
crazy.
whatever. Yeah. Physics, high school.
Yeah, that's what we learned instead of how to balance a credit card or plan our finances.
Hey, look, it finally came in handy.
Oh my god.
So I'll just say it really quick. I'm not going to even write anything about this, but 6.3,
Mhm.
which he says not to even really read, right?
Right.
It's so all that that chapter is saying is that if you replace position x with charge, like I don't know if you remember anything about circuits. If you replace position with charge, velocity with what's the time derivative of charge?
Yeah.
Currents?
Current.
Oh, very good.
And you replace this with just I dot, I guess, some other thing, right? And you replace what else? K. So M is inductance. It doesn't. No one knows what that means, so it doesn't matter.
Okay.
K is resistance. Is that true? Actually, hold on. I think that's true.
So what problem is this?
The one I'm talking about right now?
Yeah.
It's just chapter 6.3. You don't have to. I don't think it'll really matter for anything. I'm just all
Substituting. I'm not seeing where charge comes in.
6.3. No. Section 6.3.
section 6.3.
Okay.
Force with voltage. If you replace all these, now of course you can't just say you replace things. You have to make sure the units work,
Mm-hmm.
but they do. If you replace all these things, and then I don't know what maybe the damping force is. I forgot what. Hold on. I actually kind of want to know now. No, that's true. C is something. Capacitance is. What do you mean this is capacitance? And then gamma is resistance. I might have some of these mixed up, but anyway, doesn't matter. The point is that if you replace these and check that the units work, because of course it could just be like 2R, maybe you need to do, but it just happens to be if you do, maybe I actually did something wrong. Anyway, whatever. If you do this, and then for here I'm going to do F naught is V naught for some driving voltage. This gives you the exact same differential equation with the exact same solutions. Everything's exactly the same. But now, instead of saying you have a block with some forces on it of a spring and stuff, this says that you have an inductor. You have to have an inductor that's equivalent to this, if you didn't have an inductor, it wouldn't be harmonic oscillator. So you have to have that. But then if you could have a resistor and a capacitor, and then a driving voltage, constant driving voltage, or oscillating driving voltage, right? And it would be the identical. Now the point of the inductor is that it's sort of like a. Oh no, sorry, maybe it's a capacitor. Maybe this is. Okay, I don't remember. The point is that I think it is a capacitor. So the capacitor acts like a spring, because if you try to shove all the charge into one side, it'll want to restore it back. So it's kind of like the spring force, right? If you write the equations, you'll see it's voltage for a capacitor is like, I think that's right. I think that's actually what it should be. Voltage is like Q over C, right? Is that true for a capacitor? Anyway, it's something like this.
The wrong person.
And this is kind of like this. I mean, you have to make some adjustments with minus signs and stuff. And then the resistance is V over I, right? And if you just do you manipulate these a little bit, and you set instead of force, you say voltage for this whole thing, and then F equals ma is like V is L I dot. This is the equation for an inductor. Then you get the exact same differential equation, and you just get it's called an RLC circuit, right? You can also have an RL or an RC circuit. RC circuits are relatively simple. They're just like things oscillating back and forth, where they have some damping force from the resistor.
Mm-hmm.
L makes it a little more complicated. That means you have almost a resistance or an inertia to the charge. It doesn't want to change its velocity, kind of thing. That's not quite. I'm not saying that right, but anyway, something like that. And then you could also have a driving force, which is called a voltage, right? Like a voltage source. So chapter 3 is just saying that the equations are exactly the same. They even write one of the equations for, the dynamics of this. And the dynamics just means charge over time. Where is the charge? Right? If you pick one point, is the charge going this way? Is the charge, or maybe current would be a more sort of measurable thing. You could just take the derivative and you get some equation like this that would tell you how the charge goes. And maybe if it was damped and not driven, it would eventually sort of settle down to 0, right? It would, basically, the charge would stop moving if it was like constantly being slowed down by a resistor or something. Anyway, that's what 6.3 says. Okay, I'm gonna stop talking about this, and then I'll see what you want to say. Okay. Yes. Is there anything, any questions?
You guys, you're happy?
I didn't say
Well, I was
that.
gonna say, define happy.
Say that.
All right. Do you guys have anything you want to say? Any questions or anything like that?
You can have it.
Sweet. Keegan over here.
Yes.
All right. So.
Does
you
anyone
guys-
want this, by the way? I'm gonna erase all
I was
this.
just gonna.
You can grab it.
Yeah, sure.
Little snapshot. Thank you. Go. And once more for luck. Okay. Okay. So, and you guys might find some of this useful for the homework.
Yeah.
Okay. So, for number 6 points, let's start with 6.3.
Uh-huh.
All right, so for 6.3.
Yeah.
What I understand is that they want us to take this formula for x,
Mhm.
plug it into this formula, and
Yep.
prove that we get this formula.
Yeah.
Okay, here's the part of the
Well, just say what you get, because I believe 6.5 is not correct.
6.5, the formula?
The formula written in the book in 6.5 is not correct.
Okay.
So just show what you get. I mean, it's gonna be
So-
something.
Basically, my question is, how exactly, we would take the natural log of this, right?
No, you should take two. So
Take two integrals,
two derivatives.
two derivatives.
Two derivatives and then one derivative.
Two derivatives and three derivatives then.
No. X dx dt
Mhm.
on the right side of 6.4 is one derivative of that,
Mhm.
and d squared x dt squared is two derivatives of that. Sorry, I meant 2 and 1 separately.
So how would I take two integrals on this side and then
Derivatives.
How would I take two derivatives
Yeah.
on this side and one derivative on this side while keeping them both equal? 'Cause what
They're
happens-
equal because they're both forces. So there's nothing about conservation of derivatives or anything. That's not a. Don't worry about it.
So I can treat both sides with inequality. One gets one derivative.
Yeah,
one gets-
I mean, really, what you're doing is saying 6.4 is given to me. I mean,
Okay.
it's not. It's you can construct it, but it's given, and you're just filling it in. So don't think about. You're not actually doing something to both sides. You're filling in an equation. Yeah. So I think you're sort of overthinking it. It's not quite. It's not like you have to manipulate that equation.
Okay, so
You're just filling in the equation.
just fill it in, simplify it, tell you what we get. It doesn't
Exactly.
have to equal. Okay.
Exactly. What you're saying something true about you can't just take derivatives of like if you had two things that are equal, you couldn't take two derivatives of one side, one derivative of the other. But the reason you can't do that is because a derivative of x has units of like meters per second,
Okay.
and second derivative has units of meters per second squared. So if the units work, so with the way we set this up though, the units of m and the units of k are such that it's actually equal. So you're saying something true, but they've already set that up. So the definitions of m and k are such that that equation is already true.
Okay, and so in this case, we don't really need anything more than just the formulas that they outline in 6.3. It's just plug in. Simplify.
Yeah, it's just
Okay,
plug.
okay,
Yeah,
okay.
yeah.
So for question 6.2.
Mhm.
All right, so I get how to take the derivatives of these two.
Yeah.
What exactly does the r here stand for? Is that just
Oh.
a constant?
RE means real. So it's
Or any? What?
yeah. So don't just ignore the real. Keep it on. So what they mean is that if you want it. So I've been actually lying to you a little bit. When I say that this is the
Oh.
formula for this number e to the I something e to the I p, right?
Okay.
Where p is a real number. This number is not always real. This is actually a complex number.
You mean the square root of negative I, right?
That's what I mean by yeah. I is
Okay.
sorry.
So
Turn
it's
to negative 1.
Okay, so we can ignore real in this case and just Okay, so does
Yes.
that mean that the final answer for the derivative and the second derivative is just going to be real followed by whatever the first and second derivative is?
Yeah. So when
Okay.
you do all the operations, do them just inside the real,
Okay.
and at the end, I guess put the reason is because this number is this, and it works because when we take the real part, this is actually cosine of p.
Okay. So that's
So,
easy.
but technically it's a complex number, and technically we can't, like, it's kind of like it's like units, basically. You can't say my position is given by 4 plus I 5 meters. That doesn't mean anything. The answer is actually 4 meters. It's just that there's this extra piece that kind of comes along that we'll see how, I don't know how far we'll get in this, but this sometimes means something very important that you have to keep around. It's equivalent to saying that if e to the IP, I'm sorry, I'm going on like a tangent about this, but it's equivalent to saying if e to the IP is equal to every complex number you could say is this, right? And it's the real part plus the imaginary part, right? That's, well, that, right? This is literally every complex number you can always write as every number in general. You can say it's the real part of that number plus I times the imaginary part of that number. The real part of e to the I anything is cosine b, and the imaginary part of any complex number is sine. Sorry, imaginary part of e to the something. So that's this. But of course, when we do oscillators, only one of these matters. We don't actually have two free variables here. We actually only have one. So and also the other thing is, when we measure like the position of an oscillator, it's a real number. It's like 5 meters. You can't 5 I meters doesn't really mean anything. So we just take the real part of everything. But for the reason I've been doing it without writing real is because, well, the reason I've been doing it is because I forgot. But the reason that you can do it that way and you don't need to remember it really is because everything just works inside the real.
Okay.
You do all the operations on the complex thing, and at the end, when you're ready to get the answer, you take the real part. Sorry, that was a little more than. There's a long way to say you just ignore it.
It's all right. You're keeping it real.
Yeah.
We'll move on.
I was trying.
Okay. Okay. Last question.
Yes.
Then we can go. All right. So I get that for this guy right here, you take the derivative of this, you have velocity, right? So this is easy enough because sine of 1, right? That's the maximum is 0.
Yes.
Right? So that's easy enough to prove. But in this case, you take this derivative, you're going to have a cosine of the same thing, right? So in that case, it's impossible then to prove that the velocity is 0 because there's going to be something. It could be minimized, but it won't be 0. So the derivative of this is going to be a negative sine omega omega t plus b cosine, negative cosine omega naught t. So it could be negative, but it's not going to be 0.
Yeah. So the problem is that when you say that, you're sort of implicitly saying that a and b are both like 1.
Okay.
So the equation cosine plus sine is never 0. Actually, that's not true. It is 0 sometimes, but it's not. That's not what they mean.
So there's an issue with the problem then.
Actually, show that the velocity is 0 when the oscillator position is at a maximum.
I tell you what, if I just write down this is impossible for the first equation, I can go with that.
No, just use a cosine omega t. Ignore the sign.
It's dedication to that.
I can ignore the sign in this particular instance.
Yes.
Why?
Because, well, actually, I was going to say you could write it like the second one. They literally ask you for that. Hold on, let me think about it for a minute. So when you said when the position is at a maximum,
Yes.
okay, what is t?
The position is at a maximum. Isn't that relative? Like it's alright, let's see. So if we're starting from the beginning and we take the derivative of this,
Yeah.
sine, this
So
is gonna be
when the
cosine.
position is a maximum, we don't need to take the derivative. If we're just looking for the position.
Okay, if we're looking for the position, so when the position is, you said maximum?
Yeah.
Okay, so when the position is maximum, it's going to be at 0, right?
At what 0?
at t equals 0 because cosine of 0
Yeah, sure.
is 1. So that means a is going to be maximized.
Yes.
Okay.
The position is going to be A.
Position
Yes.
is going to be a.
Yeah.
Okay. Right. The next time it's going to be active is when sine is equal to 1. That's because then the value is going to be b.
Mm-hmm.
Because cosine of 1 is 0.
Okay. You're right. This is sort of a complicated problem.
Okay. I'm not crazy then.
I would say you could assume. Yeah, the reason this is a complicated problem is because the maximum of that function is dependent on a and b.
Okay.
It's actually when if a and b are 1, for example,
Mhm.
the maximum is when
It's somewhere in between the two.
omega t is pi over 4 actually,
Okay.
because sine of it's like it's 2 radical 2 over 2. Anyway, it's
But
what's
that's
that?
not when the oscillator position is at its maximum.
which is
right?
greater than 1. The reason it's confusing is okay. Yeah, you're right. You're right. It's a good point. I would just assume that b equals 0.
Okay, that's fine. That's all you have
Because-
to say.
okay,
I'm just
so
gonna
I'll
write
say
that-
this
I'm
on
just
the
gonna
video.
write- I'm just going to write this down. B is
Yes.
equal to 0.
Well, no,
Assuming
that's
B is
not the
equal to
answer.
0.
Well, I'm saying that makes the problem much easier.
No, I'm saying, like, before I go and start the derivative, I'm just going to write, assuming b is equal to 0, and then I'll just go through the derivative, and then
Yes.
I plug it in. Okay.
Yeah, so for 6.2, so I'll say this for the video. For 6.2, the first one they want you to do, assume that b is 0.
Okay.
The reason is really because this is a 3 there's 3 unknowns.
And one equation.
And one equation, and there's a solution, but it's actually way harder than any of the other ones. So I assume they don't want you to do that.
Okay.
Because for example, if b and a are both 1, the maximum is at this, and the maximum amplitude is radical 2, which is like 1.4 or whatever. This is bigger than 1, and that's really unintuitive because you had cosines and sines had to get something bigger than 1. Well, that's because you had this plus this, and so at this point, the sum was actually higher. Anyway, I don't know. It's something really. It's very complicated. I don't even know it. So I don't know. I think he meant to do something different. There's no way that's what he meant because it's very difficult.
Okay. And for, how are we going to prove this for, okay, so let's say we go ahead and we take the derivatives. That's going to be the same. Is this possible for the third equation too? So we take the derivative
Yeah.
of this, and we basically get d is equal to this multiplied by the insides of the exponent, right?
Yes.
Okay. So we go ahead and we do that, and then we say, okay, the oscillator position x is at a maximum, so that means that this can't be 0 though, right? So when this is at a maximum, yeah.
What can't be 0?
So the third equation, how do we figure out if the x position is maximum? Because it doesn't have cosine in it, and as a result, it's not a question of, is it the coefficient that's being multiplied by or 0? Yeah, so we can't really do that for this one either. Yeah.
I mean, you can,
we
but
can't.
I'm thinking of how they want you to do it. Because the thing I would say is just, oh well, if I just saw this problem, I would say, well, just take e to the I something to be cosine of that thing. But I assume that's not what they want you to do because they literally asked you that right before. I'm sorry. Yeah. There perhaps there's an easy way to do this that I'm not seeing for some reason.
Okay.
Because the way that you should do this is with taking the log, but because you have to use a complex log, you have to use.
It's a lot of work.
I'm gonna.
It's a
You
lot
have
of
to use
work.
something called analytic continuation. Because there's multiple poles in the graph of complex log.
So
There's no way that he meant for you to do any of that. So
I have a proposition.
yes.
How about if we just go ahead and say that in the interest of the fact that we understand the concept and not the mathematical principles
Yes.
behind it, we just say that this question applies to the first two equations, and that the third one we just take the derivatives? We don't have to prove anything?
I would say just write that real part of each of the I whatever is equal to cosine of that thing. That's always true.
real part of each of the I is cosine.
So this real part of e to the IP is cosine of p. And now, if you literally plug that in, you'll get the second equation exactly. So you could just say that they're equivalent because they are.
What does the P stand for again?
Anything.
Okay.
In that equation, it would be omega t plus delta.
So if we take this I P. Oh, I see. So then if we
It's-
do that, then we just get. Oh, I see.
Exactly.
So we're basically swapping definitions, right?
Exactly. So
Okay.
you literally get the exact second one.
And when
So
we
just
do that,
Just,
Yeah.
just write it's equal to this because of this.
and then we just repeat the work for the second.
Yeah, I mean you don't even have to write it. You could just say equivalent to the second one.
Oh, thank God.
Because I think I don't even. Okay, perhaps I'll later realize what he wanted you to do, but don't worry, it's fine. The point, of course, is just that you know that you must sometimes take derivatives of things with cosines and sines, and it's kind of complicated. That's what he wanted you to say.
Yeah, I got the
See.
kind of complicated part.
Yes.
All right, let's see. Before we let this opportunity slip by. Okay, yeah, that's easy.
Was it just the three?
Just 3 questions.
Okay.
Yeah, I have my rations for the day. Thank you. If anything
Yes.
else comes up, I'll send an email.
Get you on Slack.
Yes. Yeah, if you have a question for me, that's fine. But if you have a question that you think the class could benefit from, you could put it on Slack, the public
Yeah.
Slack, so people can
Yeah.
see it. Yeah.
No,
so,
I'll do that. But part of the problem is that, like, I send you a question, and if it turns out to be a reasonably easy answer or something obvious,
Right.
then I won't post it. But if it turns out to be involved something that could affect the homework, then I'll repost it
Yeah,
on
yeah.
Slack.
No, that's fine. Yeah,
Otherwise, you'll just get a 24-hour stream from me.
fair enough.
Okay. All right, I'm happy.
Good.
Thank you, Keegan.
Try my
Yes.
Thanks. Do it.
Yeah. Well, this is kind of an interesting thing, but